Okay, hi folks, I hope you're all well. What we're going to look at here is a little bit of connected particles mechanics. This one is looking at particles over a pulley. And so the idea here is, this is one of the questions that's on the sheet that you'll see in the student share drive. But what we've got here is a smooth table block with a 6 kilogram mass, whatever it is, sitting on the top of it, with a 2 kilogram weight suspended at one end and 9 kilogram at the other, by two pulleys. Now, the key words we've got here are smooth pulleys and smooth horizontal table. Now, in reality, you'll never get anything perfectly smooth, but that smooth horizontal table basically means that the 6 kilogram bit is pretty much irrelevant to everything because there's no friction being generated by that sitting on the block. The smooth pulleys also mean you're not losing anything due to friction within those pulleys. So as we just glance at that and we think about it, okay, what's going to happen? Because the first question says about showing forces acting on the three blocks, and we're going to put that down in a second. But you just got to use a bit of common sense here. There's a 9 kilogram weight at one end and 2 at the other. Now the 9 is going to beat the 2, it's heavier. So that one is going to go down. So the first thing I'm going to do is just put a little arrow just to show motion as much as anything else, direction of motion there, because that's going to be the one that's going down. Obviously this one here is going to go up as a consequence, and the block on the top is going to go left to right. So I'm just going to put that there as well. Okay, and that just gives me in my head a bit of an idea of what's going on. When it comes to actually then writing all the forces on, what we got here, the 9 kilogram will start on the right. The 9 kilogram mass obviously has a weight to it. We're just going to put in terms of G at the moment. So if we remember, about weight being the mass times G, and so in case of this, that's just going to be mg or 9g. I'll put down there. It's being suspended by the rope or whatever it is, the string, and so consequently we've got a tension going up here as well. So it's on the right, I'm going to call that T2, okay, not terminator 2, but that's the tension that's suspending that. Now, because of that, that tension is pulling it up. That's the same tension here, working in the opposite direction, that is pulling this block in the middle to the right, okay? So on the other side, we've got just a mirror image of everything. So we've got here, we've got 2G because it's a lighter block. So the weight of that block is 2G. We've got a tension coming up. We'll call that one T1 because it's on the left. Why didn't I start on the left? I don't know. And that is the same tension as pulling or trying to pull the block to the left. So there, the forces acting on those two blocks there. There's also forces acting on this one here because it also has weight. It's pushing down on the table. So what we've got there is 6G in terms of weight of the middle block. And because it's sitting on there, the actual table is pushing back up against that block. And so we've got a normal contact force, normal being 90 degrees, but the table is pushing back up at the block with the same. It's not going up or going down. So that contact force is just 6G as well. So altogether, they're the forces that are acting on it. Now, what we're going to do is work out the acceleration system and the tension in each string. And the idea is, we know there's an acceleration in the system. It's not going to be in equilibrium because it's smooth, and one of these blocks is heavier than the other. If they were both the same, it would be in equilibrium. So using my arrows, you can see that the whole diagram is showing that one's going to go up, that's going to the right, and that's going down. So we're going to use F equals ma as our key formula to help us work out what's going on. So if we start almost, I'm just going to put a 1, a 2, and a 3 here. If we start on with what's going on number 1, that block is going up. And so the idea is that the tension in the string is raising that block up in the air, so it's winning the battle. So the force is acting on it, T1 is beating 2G, and so that's the dominant force. So T1 is pulling up, the weight is pulling against, so we'll do minus 2G, and they are the forces. That is equal to the mass of the block, which is 2, times the acceleration of it, which we don't know yet, which is A. So that's everything that's going on number 1. On number 2, we've got also something happening here. This time that block's going to go down. So the weight of it, the 9G, is winning the battle. So 9G is pulling that block down. Obviously we've got the tension in the string acting against it. So minus T2. And we're going to say that's equal to MA again, but the mass of this block is 9. So 9A. Same acceleration because it's all connected particles. So we've got two things here. Now you're looking at all the different variables. We've got A, don't know. We've got T1 and T2, we don't know. All right. What I'm going to do now is just rearrange these slightly so I can put them in terms of the tension. Okay. So in the first one here, we're just nice and simple. T1 is going to be equal to 2A add 2G. And in this one, we're going to have T2. If we move it to the other side, it's going to be 9G minus 9A. Okay. And squeeze that in there. So there is obviously the third block in the middle, and that's the one we're interested in. So if we think about what's happening in the third block, it's going to go to the right, and so T2 is going to be the dominant force over T1. And so using F equals ma, yet again, we're going to have T2 minus T1, and that's going to be equal to the mass of that one, which is 6A. Now, of course, now I'm thinking, but hold on, I know what T2 and T1 are. And so in terms of those, what we're going to see now, if I swap them in, we'll have 9G minus 9A. And then we're going to take away T1, so minus 2A minus 2G equals 6A. So I've tidied that up a little bit. 9G take away 2G is 7G, minus 11A equals 6A. And so we've got 7G is equal to 17A. And so now we know what the acceleration is. A is going to be equal to 7G over 17 meters per second squared. Okay, and so you can leave it in that, or you can just say, okay, if I want to put my 9.8 in, so 7 times 9.8 for G divided by 17. Okay, it's 4.0. So if you want to put that, 4.0 meters per second squared. So that gives you an idea of the acceleration. Of course, because we did the hard work of rearranging these here at the top, we can now quickly work out what the tensions are. And so T1 is going to be 2A, so 2 lots of this, so 2 lots of 7G over 17 plus 2G. If we just tidy that up a little bit, so what's that going to be? 14G over 17. 2G, so we'll put that into 34G over 17, so we've got a common denominator, so 48G over 17, and that's going to be in newtons. Again, if you want to type that in, we can do that. 48 times 9.8, and then we're going to divide by 17, 27.7. Okay, so we can have that in terms of newtons, and it's no harder to do T2 as well. So that's going to be 9G take away 9A. So that was 7G over 17. Just tidy that up. So 9G, what's 9 times 17? We tidy that up a little bit, 153. 153 G over 17, take away 63 G over 17, gives me 90G over 17. And if I just type that into my calculator as well, 90G divided by 17, that gives you 51.9. That gives you overall the two forces or tensions in the string. Obviously we can see that one has a greater tension in the string because that's what's pulling this one down. It's got a heavier weight on it, and that makes common sense. Okay, thank you. Next question coming soon.